In this video I'm going to go through some motion questions. Now some of these questions are tied into forces and motion. I'll skip over the forces part and just directly talk about the motion part, so more specifically motion graphs and calculating velocity and acceleration. This is just to help with anyone that had some questions to do with motion graphs. So this question says, the graph shows how the velocity of a small car changes. So we've got time, okay, and we've got velocity on the y-axis. And so initially, this car is at rest, okay, so at 0 seconds, it has no velocity, it's not moving. But then what happens is, as the time increases, the velocity of this car increases up to a maximum velocity of 20 meters per second. And this straight line represents that for every second that you go along, you go up by a set amount. Okay, so your change in velocity goes up by the same amount each second. In other words, the gradient of this line is telling you your change in velocity over the time taken, and change in velocity over time is acceleration. And as it is a straight line, this is uniform acceleration. Then when it reaches, what's this, 1, 2, 3, 4, 5, yeah, so when it reaches 5 seconds, although that's not on the scale, it's going up in twos, so this would be 6 and this would be 8. So I may as well just pop that in. So that's 6 seconds, that's 8 seconds, and this is 5 seconds, halfway between 4 and 6. So for the 5th second, it's reached its maximum velocity, and it's now going to maintain that constant velocity, okay, for the next 3 seconds, from 5 seconds to 8 seconds. And then after that, it's going to decelerate. Notice the steepness of the graph means that the deceleration is larger in magnitude than the original acceleration. It took 5 seconds to get up to 20 meters per second, but it's only going to take 2 seconds to decelerate back down to 0 velocity. So it'll stop after 10 seconds. Right, so the questions. It says, complete the sentence by putting a cross in the box next to your answer. The resultant force on the car will be 0 when the car is... Okay, so I wasn't going to talk about forces acting on objects, just the motion itself, but we can fill this in if there is... so let's read again. The resultant force on the car will be 0. So when the resultant force on the car is 0, that means that the car will be moving at a constant velocity. The only way it's going to change that velocity is if it accelerates or decelerates, and that would require a force. Okay, so there will be forces acting on the car. So this is now just me talking about forces, which I said I wasn't going to do. But if this car has an engine force that drives it forward, and that is matched by the drag forces, that could be the air resistive forces, the frictional forces between the tyres and the road. But if these forces are equal in size and opposite in direction, they are balanced, and so overall there is no resultant force, okay? And you need that resultant force to cause it to accelerate or decelerate, so it will maintain that speed. If you want to get faster, you're going to have to put your foot on the accelerator and increase your engine force, or if you want to decelerate, you're going to have to put your foot on the brake and increase the drag forces, the frictional forces. Okay, B. Use the graph to estimate the velocity of the car at 3 seconds. Okay, so we're going to estimate the velocity of the car at 3 seconds. It's suggesting estimates probably because it's going to be fairly difficult to say just from halfway. I'm not going to use a ruler and measure this out. So this is at 3 seconds. And then as we go along, what's this going up in? 5, 10, so that'd be 12.5, okay? So it's reached 12.5 meters per second in 3 seconds, okay? And that would be my estimate, okay? Somewhere, I'm sure the answers should be somewhere kind of like between 12 to 12.5 meters per second. And really I should use a ruler on this, but you can see what I've done. At 3 seconds, you go up to the line and then read directly off the y-axis that'll tell you the velocity. Okay, oh. Next part. It says, calculate the acceleration of the car when it is speeding up. Okay, so we're going to calculate the acceleration of the car when it is speeding up. So just go back to this. This is the part where it's speeding up, it's increasing its velocity, and it does not matter how we work this gradient out, just as long as we work the gradient out in terms of position. You could say how far up have you gone in 2 seconds, in 4 seconds, in 5 seconds. Okay, it's easier to take a gradient going from two very large points, okay, so a long part of the line rather than a tiny little bit. That's difficult to do. So what I'll do is I'll just work out the entire gradient of the line in the 5 seconds, increasing by 20 meters per second. Okay, so I mean that the acceleration on a velocity time graph is the gradient of the line. And the gradient of that line means what is the change in velocity in the y-axis over the change in time, or the time taken to change that velocity. And if you can remember, it went up to 20 meters per second in a time of 5 seconds. So that would be 4 meters per second squared. This is our unit for acceleration. Change in velocity, 0 to 20 is meters per second divided by seconds, meters per second squared. It's already got it there, so you don't even have to think about that. So there we go, 4 meters per second squared. Explain why the units of acceleration is the meter per second squared. Well, it's a change in velocity, which is in meters per second, and then that is divided by time in seconds, so per seconds again. Okay, so you could write out as meters per second, and mathematically that just means meters per second squared. Show that the car travels further at a constant velocity than it does when it is slowing down. Right, so what we need to do then is we need to take a look at our graph again. So I'm going to go back to the graph. Okay, and we need to calculate, so it says show that it goes further at a constant velocity than it does when it's slowing down. So in other words, we need to work out how far it travels when it's moving at 20 meters per second for these 3 seconds, and compare that to how far it travels when it's decelerating from 20 down to 0 meters per second in 2 seconds. Okay, now, as discussed before, it's the area under a velocity time graph which will tell us how far we've moved. Okay, if velocity is the distance divided by the time, then the distance travelled would be velocity times time, which is fine for when you're going at constant velocity. However, if you're changing your velocity, it's still the same principle. We work out the area, but the area of this shape is a triangle. So we're going to work out the area of A and compare that to the area of B. So I'll keep referring back to the numbers here. So we've got the area of A, which is just a rectangle, which has a height of 20 meters per second and a base width of 3 seconds. Here's the figure, that's 20 by 3. And notice if you multiply meters per second by seconds, the per seconds times seconds cancel, and you will be left with a unit, the meter. So we do know what the area is, the distance travelled. So that's 60 meters. And then if we go back and have a look at 2 seconds decelerating from 20 down to 0, this is the area of a triangle, and the area of a triangle, so area B, will be half the base, which is 2 seconds, times the height, which is a change in 20 meters per second. So if I half times 2 is 1 times 20, that's going to come out as 20 meters. Okay, and it says show that the car does travel further at a constant velocity when it's moving for 3 seconds at constant 20 meters per second than it does when it's slowing down. Okay, so it travels a whole 60 meters in those 3 seconds at constant velocity, and it only travels at 20 meters per second when it's decelerating over 2 seconds. Right. Next question. So it says a crane is lifting a heavy block from the ground to the top of a building. This is the velocity time graph for the block as it travels upwards. So this block initially is at rest, okay, it tells us here, and then it suddenly accelerates. I know that because I've got this this line, it's a straight line, so it means it's uniform acceleration. It means that the rate at which you go up in speed is constant, and for 2 seconds it gets up to its maximum speed of 3 meters per second. So it accelerates up to 3 meters per second, and then from 2 seconds all the way to 20 seconds, so that's 18 seconds. For 18 seconds it's constantly moving at that 3 meters per second. And then just before it reaches the end, it's going to decelerate, and it takes 2 seconds again. So the rate of deceleration is the same in terms of the actual gradient, it's just the direction of that gradient. This is increasing speed, this is decreasing speed. Acceleration, deceleration. And the question says, for how many seconds is the block moving at constant velocity? Okay, so constant velocity starts at 2 seconds, and it goes up to 18 seconds. I said 18 overall. Okay, sorry about that, an oversight. It actually travels for 16 seconds. The difference between 18 and 2 seconds, so 18 minus 2 would be 16 seconds. Okay, so that's how long it's traveling at constant velocity. Okay, final page. I think it looks like we start with a forces question, but then towards the end there's an acceleration calculation. So this says that the diagram shows one of the forces acting, so this is the upward pull from the cable. Draw an arrow on the diagram to represent the weight. Okay, so that's going to be the upward pulls balancing out the weight of the object when it's moving at constant velocity. Complete the sentence by putting a cross in the box next to your answer. When the block is moving upwards at a constant velocity, the resultant force on the block is, well, we talked about this with the car, there's zero resultant force because it's reached a maximum velocity, so it's accelerated up to that velocity and now it maintains that velocity because the forces are balanced. The up force is equal but opposite to the down force. So the tension in that cable is equal to the weight but in the opposite direction. Final question. Use the velocity time graph to calculate the acceleration of the block during the first 2 seconds. Okay, so acceleration would be a gradient of line. Okay, so the acceleration would equal the gradient of the velocity time graph line. Let's just refer back to that graph. Find it. There it is. I threw it on the floor. So it wants us to work out the acceleration in the first 2 seconds, and it increased its speed to 3 meters per second. So the gradient of the line would be the change in the y-axis, which was 3 meters per second, and the change in the x-axis, which is the time base, is 2 seconds. And 3 divided by 2 is 1.5 meters per second squared. So the answer is 1.5, and the unit of acceleration is meters per second squared. Okay, I hope going through some questions has helped. We'll leave it there.